Okay, so good afternoon, everyone. Welcome to the Tech Talk series, which is co-organized by Hong Kong U and the Hong Kong Academy of Engineering Sciences, and also supported by the Innovation and Technology Commission of Hong Kong Government. Today, we are very happy to have Professor Alfonso Nguyen to give us a talk on some impressive metallurgical issues in the water supply in Hong Kong. Professor Nguyen is the Kingboard professor and the chair professor in the Department of Mechanical Engineering, and also is now the vice president for academic development for Hong Kong U. And before joining Hong Kong U in 1993, Professor Nguyen got his PhD from University of Birmingham, followed by a one-year postdoc training at Oxford University. Professor Nguyen is the recipient of many prestigious prizes and honors, such as the Culture Senior Research Fellowship and the Grand Prize of Hong Kong Institute of Engineers, and also Changjiang Professorship. And also, Professor Nguyen is an elected fellow of the Royal Academy of Engineering and the Hong Kong Academy of Engineering Sciences. Okay, so with that, let's give a big welcome to Professor Nguyen.
Thank you. Thank you very much, Professor Lin. Thank you, Professor Lee, for organizing this, and thanks for coming to this last talk of this season of Tech Talks. In the following hour or so, I will be talking about our research. Which one is the laser pointer? First one. I'll be talking about our research actually sponsored by Water Supply Department as well as the Research Impact Fund in the RGC. Two aspects that I'll be talking about. If you read the abstract, the story is written there. So in Hong Kong, of course, the authority supplies fresh water, potable water, but because we also use seawater for toilet flushing, and this is actually a rather unique system in the world. So therefore, the Water Supplies Department supplies two types of water, fresh water as well as seawater. And I am going to talk about what kind of metallurgical issues are involved in the piping system in these two types of water delivery. Okay, so this is a slide that I borrowed from this author. So basically, this is just about wastewater from domestic usage. So it shows that in a typical setting, in terms of wastewater, so that's not a small fraction, as you can see, 25%, it may be 30%, right? So this is worldwide, actually, not limited to Hong Kong. And for people of my age or even senior, we would remember those days, 1950s, 60s, where we suffered from rather serious droughts. In those days, people lined up for fresh water supply, which may come perhaps once a week or even less frequent than that. So that actually was the background or the backdrop for the more massive use of seawater for toilet flushing. So winding the clock fastward to today, WSD still doesn't work, supplies this amount of water, more than 300 mega meter cube of seawater annually. And that is about 1/3 of the annual freshwater consumption. So in other words, if we use seawater to do toilet flushing, we'll be saving that amount of fresh water that otherwise we have to supply by reservoirs and also maybe the Dongjiang River water. But that was in the 60s and 50s, as I said. So the question is, why does this seawater flushing for toilet flushing system continues in Hong Kong till today. Well, basically, this is a very busy graph, but I just took it from the WSD website. And this is our very stringent WSD hard work or efforts on trying to keep up the high standards for fresh water, okay, for drinking water. So day in, day out, they are testing 57 chemical parameters. Those in the red frames over here. So if you read through them, those are lots of chemicals that they are testing for us, just to make sure that the water that we drink is safe enough. And furthermore, 2 more radiological parameters, alpha beta radiation, and the E. coli as well, as the microbiological parameter. So drinking water, of course, is under very stringent control. Our WSD make sure that by testing all these chemicals and parameters, the water that we drink is safe. But obviously for flushing water, we don't need that type of high quality. If we use the same type of water as is done in other jurisdictions like the UK, right, we'll be wasting a lot of resources. And bear in mind, it's 1/3 of the total consumption. So these 2 tables shows the comparison between the water quality objectives for salt water, i.e. seawater, versus drinking water. So there are certain parameters that may be compared, like the color for seawater for toilet flushing. We just require this amount of threshold, right? But for drinking water, obviously, color is less than 15, a lot lower. Another would be, let's say, turbidity. In this, NTU 20, but for drinking water has got to be less than 3. Actually, the international norm is 5, so Hong Kong is even more stringent than international. And some other parameters are the same. So in other words, using seawater for flushing, we can reduce costs, energy consumption, and of course, carbon footprint, right? And actually, our seawater flushing system has been praised or admired quite a lot in other places. So I just grabbed out 2 recent news reports. That one is from Singapore, the Straits Times. So they were talking about opening their 5th desalination plant. And then this person, this KOL was talking about, oh, that's perhaps not very energy efficient. And just look at Hong Kong, for example, cities like Hong Kong, we have been using seawater, and that's quite a success for so many decades. So that's an example that they were referring to. And this is another one from the Middle East, I suppose, King Abdullah University. So in this study, they were studying the effects of bacteria on nitrogen and how the effect of seawater would be on the bacteria on removing nitrogen. But they were doing that sort of research in the context of also using seawater for toilet flushing. And they were also referring to, as you can see, Hong Kong, Singapore, Tokyo as using this system. This is a slightly earlier report, a decade ago, carried out by colleagues in HKUST. So they were talking about the cost effectiveness of changing toilet flushing from fresh water to seawater. And their conclusion is that not all cities would be able to benefit from that change. Only densely populated cities and those with lower construction costs may be able to benefit. So places like Hong Kong obviously is one, but a lot of densely populated cities like some of these in India or Buenos Aires, Jakarta would benefit from. Singapore is another example that would benefit from. Shanghai as well, so coastal cities, but also densely populated. But other places like LA, Miami, and some other cities would not be that cost effective. So it's not a system for everybody, But still, there are quite a lot of cities in the world that would be able to benefit from that. So those are the good things about using seawater, but obviously the problem is that if you immerse metals in seawater, or if you use metallic pipes to transport seawater, then obviously corrosion is more serious. And well, just looking at the system in Hong Kong, we have been using that for many decades, 7 or 8 decades. So gradually, pipe aging problems occur and associated with a lot of water main bursts. Okay, so this happened just outside the west gate of the university. So when a pipe bursts, you can see how damaging that could be. And WSD annually spends 100 million, right, on trying to repair all these pipes. And of course, that amount does not include the indirect economic losses due to collapse of the road resulting in disruption to business or traffic and things like that. So in fact, the situation was serious enough to alert the ombudsman unit of the Hong Kong government to carry out studies a few years back. So in about 2017, 2018, they carried out 2 direct investigations and 1 full investigation. So those are data extracted from one of their reports. So sorry that these are in Chinese, but basically different years and then the different number of water main bursts. And this first table is for freshwater pipes. The second table down there is for seawater pipes. And then I took these data and plot them into this graph. And this straight line is the one-to-one line in the different years. So the years went from 2012 to 2017. So gradually, the number of water pipe burst cases is reducing, which is good, right? But this may perhaps be due to the fact that we are gradually replacing some of the problematic pipes, and therefore, you know, as you migrate to more recent times, then the pipe burst would die down a little bit, but it may be a cycle. It may come back. We don't know. The second interesting observation is that the data actually fall on this one-to-one curve. All right, so number of seawater pipes bursts, a number of freshwater pipe bursts, and they are highly correlated, and it's actually not difficult to understand why, because these are buried together. So when, let's say, a seawater pipe bursts, road would collapse, and that perhaps would knock out the other type of burst. So basically, if we anticipate that the seawater pipe are more susceptible to corrosion, the effect is not just on the seawater pipes. The burst would also affect the freshwater pipe. So the high correlation actually is also a concern, right? So what could be the potential solutions to slow down or control the aging of the seawater pipes? There could be a few that could come out from the top of my head. Well, many people would say that, oh, why don't we replace pipes with more corrosion-resistant materials, stainless steel, for example. Well, cost is a concern, and there are other concerns as well. The second would be, oh, why don't we use robotics, AI, to do monitoring, all right? Or thirdly, can we add some drugs or chemical inhibitors to the water, to the seawater, so as to protect the pipe surfaces? Now, of the three, a constraint is that the total length of seawater carrying pipes in Hong Kong amount to this sort of magnitude, 1,683 kilometers. And how long is that? That could take you from Hong Kong to Shandong, to Qingdao. So very long. All these long length is packed within a very small city, and that's our Hong Kong, right? So if you have so long a total length to take care, and if you consider these possibilities, you can quickly rule out the first two, okay? Replacing with more corrosion-resistant materials, far too expensive. And if the pipes do not burst, you don't want to dig up the road and do the repair. Why do you want to do that? You would disrupt the traffic, okay? Robotics AI is a nice final year project maybe, but it's not that practical to have a robot walking along the pipe just to do inspection, to see, to detect where are the potential fracture areas. Is a nice scientific work, but it's not engineering sensible. So perhaps the only solution that we could think of would be the third one, which is you add drugs in the water to be transported. And then the water would then carry the drug and spread it over the entire length of the pipe surface and try to protect the surface. So we were then given this project by the WSD a few years back during the pandemic, so the work wasn't easy at all. So WSD generously funded this project and asked us to build a high throughput test rig in one of the seawater or saltwater pumping stations. That's actually in Sandy Bay, quite close to our campus. So that was the real look of the test rig. And in the test rig, of course, we pump water from the sea nearby just before the water enters into the system that will be fed into the customers. And then along the pipeline, we have a certain number of these specimen holders. So there are these compartments, and in each compartment, we can mount a lot of metallic specimens. So the metallic specimens are typical metals for making the pipes, including ductile iron, cast iron, mild steel, stainless steel. In Hong Kong, we don't actually use that much of stainless steel because of the cost, but just for comparison, we also did that. So mainly for real applications, we use ductile iron, cast iron, and mild steel. Okay, and then that was the test schedule. As I said, the study took place during the pandemic, so it was not easy, but we managed to finish the project. So those were the immersion periods ranging from a month to, let's say, close to a year. And then we added different chemical inhibitors, say calcium hydroxide, lime, basically that is what that is, at different concentrations, okay? So ranging from 5 to 25 milligrams per liter, as well as sodium hydroxide, calcium gluconate, sodium polyphosphate, and of course the control without any chemical inhibitor added. So that's just the pure seawater. So those are the typical results. Of course, we generated lots of results for different conditions. So this is just to show a typical set of results for 25 milligrams per liter of calcium hydroxide for different materials, and as well as the control, which is without the inhibitor. And as you can see, for each metallic material, let's say if you take ductile iron, okay, if you have the, which is the black curve, if you have the calcium hydroxide added, the corrosion amount, so we measure the corrosion by the weight loss. So after the metal has been immersed, we took it out, polish off the rust, and measure the weight. So the difference in weight before and after, in terms of percentage, would be this scale, and the horizontal is the immersion period. So let's say if you look at ductile iron, if you have the calcium hydroxide inhibitor, the corrosion amount is only that much, but then without the inhibitor added, ductile ion would be this gray curve. It will be up there. Okay, so there is this much of difference for about a year. So in other words, adding this inhibitor would slow down the corrosion, would basically reduce the corrosion. In this sort of business, there is an indicator which is called the inhibition efficiency, defined as the corrosion rate without the inhibitor, which will be higher, minus that with the inhibitor, which will be lower, and convert that to a percentage. Okay? So this IE basically tells you how efficient the chemical inhibitor is. And for any inhibitor that works, that will slow down the corrosion, V0 should be larger than V, as I said, and therefore this IE would be positive. So as long as you see a positive value of IE, that inhibitor would be able to slow down the corrosion. Okay? So basically in all the conditions that we have tested, that is the 0 mark. So most of the, I would say majority of the data that we have tested show that the inhibitors will be able to slow down the corrosion for different materials as well and different durations. Okay? And if we assume corrosion to the end, so no pitting, no cracking, so you take a slab and then let corrosion to reduce the thickness to the end, this ideal condition, if IE is 0.5, so that sort of value, which is not uncommon from our data, the improvement in lifetime will be doubled. All right, so if you have an IE of 50%, that means that your metal will corrode with a lifetime of 1 time more, right, or twice the original. So that's the sort of idea of the significance of this IE. Okay, so basically our full-scale test, not full-scale, but the plant test shows that in a lot of the chemical inhibitors, the effect is not good, not bad, it's quite good. But of course, another concern is the turbidity. I mean, after adding the inhibitor, would it deteriorate the turbidity? The answer sometimes is yes, but for this group of inhibitors, the calcium hydroxide, in fact, the change is very, very small. Okay, so those are the real picture. This is the control without adding the calcium hydroxide, and then different amounts of calcium hydroxide. The water is nearly as clear as before. Okay, in fact, the change in turbidity is within the noise, I would say, and is far below the WSD objective of less than 20 of this NTU. All right, so that's a good sign. Okay, so those were very encouraging results, and of course that led us to dig deeper into what is actually the science behind, right? What is the inhibition mechanism? So a very simple picture for corrosion or ferrous material is that there should be an anodic reaction. So for that, the iron will oxidize into iron 2+, and then losing 2 electrons. The 2 electrons will be fed into the cathodic site, where the cathodic reaction will happen. So typically that would involve converting oxygen into water by absorbing the electrons from the anodic site. Okay, and then the generated ions will then react with oxygen to form your rust. Okay, and typically we were interested in this interface between the metal and the water, the seawater, for example. Okay, and usually we would model this interface by this equivalent electric circuit. comprising some resistors and some capacitors. Okay, so that's more or less like the textbook picture of corrosion of ferrous materials. So we want to dig deeper into that sort of science, starting from that kind of scientific picture. But the problem is, with using real seawater is that real seawater pumped out from the ocean is very varying. There are a lot of variables which are hard to control, and therefore the results won't be very repeatable. So for that, we switch to simulated seawater, SSW. So there are standards around where you can mix up chemicals to form this sort of SSW, simulated seawater. Okay? And because all the conditions are fixed, so at least the water itself is not a variable. So for this scientific study, we just keep the inhibitor condition to be 25 milligrams per liter of calcium hydroxide. And also we focus on just one type of steel, which is a very common pipe steel, Q235 pipe steel, with compositions listed in here. So the question that we have in mind is, okay, we're adding lime. This is calcium hydroxide, which is lime, right? We add lime into the seawater. Is the explanation for the corrosion protection due to the change in the alkalinity, right? If you add lime into water, you make the water more alkaline. And if you make the water more alkaline, let's say this is the corrosion curve for a typical metal, let's say magnesium, right? So in the magnesium, again, there will be an anodic reaction, which is like this. The magnesium will oxidize into magnesium ions. And there will also be a cathodic, where just like what I've shown before for the steel, the water will change into hydroxide. Therefore, if you add these two, the overall reaction will be this. So if you add more lime, add more OH2, you basically will drive the equilibrium of this reaction towards the left, and that is you would slow down the reaction. That is one, in fact, the very first mechanism that our WSD colleagues thought of. Okay, so when they saw our result, they say that, oh, it's obvious because you add lime into the water that will make the water more alkaline. That must be the mechanism. And we thought that was the reason as well, until we carried out a more detailed study. And actually, we found that for the amount of lime that we have added, which is this amount already, 25 milligrams per liter, the change in the pH value is minimal. All right, so this scale is largely magnified. All right, it doesn't start from zero. Okay, so the control is that value. Without adding the lime is that value. Adding the lime, of course, the pH will go up, but just by a very small amount. It goes up from 8.3 to 8.8 something, so point something pH, which is not great. And actually, for increasing immersion duration, the one with the inhibitor has the pH drops. Okay, so the pH cannot be a reason. And another way of seeing that is that if we look at the potential stat or polarization curve, the red is with the inhibitor, the blue is without the inhibitor, and this tip over here, separating the anodic branch and the cathodic branch, this tip over here is what people call the corrosion potential, the ECORR. You can see that for the two conditions, they have the same ECORR. So in other words, the change is not due to a change in the corrosion potential. You do see that the corrosion current decreases after adding the inhibitor. So the corrosion no doubt slows down, but it's not due to a shift in the corrosion potential. So the pH cannot be a reason. So we had to dig deeper then in order to find out what is the mechanism. So just to go back to that interface that I was talking about, the metallic and electrolyte interface, this one, right? As I said, people usually use this sort of equivalent electric circuit to model the charge transfer across that interface. So what could be the resistor or what could be the capacitors represent? Basically, in the atomic picture, all right, the capacitance or capacitor arises from electric double layer. All right, so if you have a clean metallic surface and if you charge the metallic surface with respect to the electrolyte, you would encourage the generation of a layer of double charges. That is what people call EDL, electric double layer, in the electrolyte. So once you have this dipole layer, it looks like a capacitor. It behaves as a capacitor, all right? Another possibility for the charge transfer would be the redox reaction, the oxidation reduction that we talk about involving charge transfer. And people usually model that by putting a capacitor and a resistor in parallel. Okay, so that's why in that model you have this one, the capacitor and the resistor in parallel. That would be the charge transfer, and this one is just perhaps the electric double layer. Okay, you also have other resistors for just pushing charges through the liquid or through the let's say the corrosion product film. Okay. Now, if you oscillate the voltage between the electrolyte and the metal, and then you do what people call an electrical impedance measurement. So the voltage and the current, they are now AC, not DC. Okay, so when you change when you oscillate the voltage, the current will also oscillate. So there is an impedance between the two, and there may be phase lag between the two as well. So the impedance is actually an imaginary number, going back to our basics. For pure capacitor, we know that the impedance is purely imaginary. So in the Nyquist plot, it will be a vertical line. But in the case of putting a capacitor and a resistor in parallel, that plot will be semicircle. Okay, so just by looking at the electrical impedance plot, we can basically understand whether it is EDL or whether it is pseudo-capacitive charge transfer, which is the redox. So that was the theory. Those are the real results from our simulated seawater test. So you see a lot of semicircles, but they are not exactly semicircles. Okay, so obviously there will be a strong effect from this redox reaction, but they are not purely semicircles. So some other elements have got to be there in order to explain the shapes of these impedance plots, the Nyquist plots. So just by fitting these parameters, we were able to sort out the so-called RP, which is the polarization resistance, which is the sum of this resistor plus that resistor, right? The resistance in the product film as well as the resistance in the interface. So that total sum is called the polarization resistance. So the red is with the inhibitor, the blue is without the inhibitor. So as you can see that for a short duration, after a week or so, the polarization resistance with the inhibitor actually becomes larger. Okay, so that explains why corrosion is smaller or slower. You can also look at CF, which is this the capacitance of this capacitor, and for that, the CF for the inhibitor group becomes smaller. So that indicates that, well, the resistance is inversely proportional to the thickness of the gap of the resistor, right? So when the CF is smaller, that means that the gap here, or the spacing, or the width of this product film is larger with the inhibitor. Okay, so the inhibitor actually supports the growth of this so-called protective film or product film, which we will also understand what exactly that is later on. And the CDL, the double layer, this one becomes rather steady. Okay, so that is not a varying factor. So to understand what exactly is this product film which grows with time, with the immersion time, we also carried out microstructural studies as usual from metallurgy like myself. Well, without going into the details of all these XRD analysis and things like that, just to conclude that we identify rather continuous formation of calcium carbonate. Okay, and then the possible reactions for their generation are listed in here. Okay, so basically you add this calcium hydroxide, and that reacts with CO2, carbon dioxide, turn into this, and that at the cathodic site supports the formation of this calcium hydroxide. Okay. So you form a scaling layer of this calcium hydroxide, which leads to thickening of that layer, reduction of the CF, and also growth of the RF. Okay, this one. So we also took the chance to recalculate this inhibition efficiency, not from the weight loss measurement now, but directly from the corrosion current, which could be related to the slopes of the anodic and cathodic branches, which are called TEFL slopes. So these are what these beta are. And then the calculated values are all in the range of 20-something% to 30-something%. And they are pretty steady. Okay, again, they are positive, indicating that the chemical can protect the metal from corrosion. Okay, finally on this part, how effective is it to use that kind of drug, calcium hydroxide that is, okay? So we're looking at, let's say, Alibaba or Taobao, right? For calcium hydroxide, it costs about 4 Hong Kong dollars per kilogram. Okay, and then we are not going to use 25 milligram. The 25 milligram per liter was just for scientific study to speed up the study, right? We are only recommending 5 milligram per liter. That was also good enough. If we go back to look at this graph, the 5 milligram per liter, that will also give IE values of 20% or more. So that is good enough. And in Hong Kong, I said before that we use that much of, or we supply that much of seawater per year, okay, 320 mega cubic meters. So therefore, the cost per year, the material cost per year would be about 6 million. Well, that may sound high to you, but it's actually not that high compared to the annual operating and administration expenses related to flushing water supply. That's just 0.6% of the cost that WSD uses annually just to operate and administer the system. Or if you talk about the water main repair works that I mentioned earlier on, I mentioned 1 億, right, 100 million. So that is only about 6% of it. Okay, so it's quite cheap compared to if you just let the pipes to burst and then do the repair. Okay, so that was my first topic. The second topic was lead leaching in potable water, drinking water. So we leave seawater now, go back to the water that we drink, and look at what sort of issues, metallurgical issues, could be associated with that. So we go back to these parameters that our WSD tests for us every day to make sure that our drinking water is safe enough. So among the 57 chemical parameters, one important one, as you can imagine, would be lead. Okay? So the guideline is to have the lead lower than 10 micrograms per liter, which is also the WHO guideline. What dragged us into this study was this incident a decade ago in Kaixingchun. So newly completed housing estate where there were consistent reports of lead leaching in potable water. And of course, the government formed an inquiry, and this is our old colleague, Dr. Green, if you remember him. So he was there helping as the chief metallurgist of the study group, investigation group. And they concluded that somehow the contractors have used illegally, used lead-containing solder materials to do the pipe joining, right, soldering. However, lead is always present in copper or brass. Okay, why? I will tell you why later on. Okay, so even though they have WSD, I think since then has tightened the control. For example, they have developed this GA system, the so-called general acceptance system. So nowadays, just like buying a fridge or a washing machine, there are these energy efficient labels, right? Similarly, if you want to buy some water supplying components, there are QR codes attached, you can scan, and then WSD will tell you whether the product is safe or not. Okay, so that's their excellent GA system that they have developed. So that should be one big step forward to make sure that your piping materials are up to standard. Okay. So going back to lead, I said that it's almost impossible to exclude lead in copper. So-called the lead dilemma in copper pipes. So first of all, lead present in water-carrying materials is not desirable because, as we know, lead is harmful to us. They can cause neurological damage. They can affect, women, pregnant women, and things like that with very nasty outcomes. So that's why WHO has this guideline of 10 micrograms per liter, which, of course, our WSD is trying to keep. However, why don't we have zero lead? Well, we have to have some lead because the lead is there to make sure that the material, the copper or brass, is machinable. Okay, so I'll come back to this point later on. Okay, so even the so-called lead-free grade of copper or brass is not actually lead-free. Okay, so those are what people call so-called lead-free, but basically the standards still allow certain amount of lead present. So that would be the different percentages for different components, valves, taps, and pipes and fittings. Okay, so why lead has got to be in the material? As I said, it's there to ease machining. So this is not our work. This is some work published 2 years ago by this group. Okay, so this is brass. Copper zinc is brass, as we can see. The first one is without any lead, so pure brass. And this one is brass with 3% of lead. For the first one, you can see that the chips are continuous. And then the machine surface is rather rough. For the second one, the chips are discontinuous. So they fly off one after another, and then the machine surface is very flat. Okay? And in terms of the cutting resistance, if you have lead, the resistance is lower. In terms of the temperature generated, so you move a tool to cut the metal, of course the tool will become hotter, or the surface will become hotter. Okay? But if you have some lead present, the temperature rise is smaller. Okay? That is because the lead present in copper is not miscible. So the lead, as we'll see some nice pictures later on, the lead is always present in terms of particles, and these particles, they separate out the matrix, and therefore they make sure that the chips are discontinuous, and therefore the cutting is more clean and clear-cut, right? So if you are a technician, for example, doing machining work, you would love to have lead present in your brass or copper. If I give you a piece of pure copper, pure brass to cut, it's a nightmare to cut. So that is the fact, right? So in the industry, it's almost impossible to make sure that you use pure brass or copper in delivering water. And this is as a result of that Kai Ching incident. A few years later, we produced this paper, and we were looking into the thermomechanical processing, how that would affect the lead leaching. So as you can imagine, in the work site, people need to do this sort of operation. They need to cut the pipes and perhaps join them, right? So there is mechanical cutting as well as some polishing, or you can also do soldering and brazing, okay? So we were looking at how these processes would affect the coming out of the lead from the brass. So in the laboratory, we did some scratch tests. So we use a scratching machine. So those are the scratch tracks, okay? And then we use different scratching forces, and we use different number of cycles. The white bits were identified to be lead particles, okay? So as you scratch a copper surface or brass surface, basically the lead will come out, all right? So that shows the result. So for example, this green curve shows that the lead coming out would increase with time, okay? And not just mechanical machining. As I said, you can also heat up the brass as you do soldering or brazing. So in the laboratory, we use two temperatures to simulate these two processes. So 200 degrees Celsius to simulate soldering, and 700 degrees Celsius to simulate brazing. And we found that after heating up the brass and then immerse the brass into water, lead again will leach into the water, okay? Of course, it will leach more if we heat up the material for longer durations. So the thermomechanical processing is an important factor leading to lead leaching. So arising from that, this one is not supported by Research Impact Fund. So we built a high throughput test rig. This time not in a pumping station, but again in another site supplied by or provided by WSD. So we built these test rigs, and in each one we have water, now fresh water, not seawater, and then we would have some brass component immersed inside. And by this test rig, we can study a lot of different conditions. So for example, the effect of polishing, the effect of preheating the workpiece, the water flow rate, so on and so forth. So that's our study scheme. And that's also part of the study scheme as well. So we have different polishing conditions. We have different heating conditions. We have even different flushing effects. So either no flush or strong flush or weak flush, or even replenishing intervals. And those are just snapshots of some of our results. So for example, for the flushing effect, if we flush strongly, then more lead will leach out. Or for the surface roughness, if we polish more, right, then the lead leaching will be slightly higher in this case. For the temperature, if we heat with a high temperature, then more lead leaching will occur. All right, so So now we know that lead will come out, and especially if you heat or cut or polish the material. But we also wanted to know the pathways. So as I said before, lead is completely immiscible in copper, right? So we subjected some of these pieces to X-ray using this synchrotron facility in Beijing. And the blue stuff is the lead. The black will be the copper matrix, right? So you can see that basically the lead is present in terms of particles, but if you heat the metal at a lower temperature, 200 degrees Celsius, the particles are more spherical, they are more rounded. But if you heat up at 700 degrees Celsius, the brazing temperature, the particles, so-called particles, become more sheet-like, right? So the asperity, sphericity reduces. So at the lower heating temperature, for let's say the soldering condition, as I said, you have these particles, rounded particles, and a lot of them actually are at triple points between grains, so-called the triple point grain boundary junctions. Okay, so after heating at 200 degrees Celsius, so the lead would not melt at this temperature, right? Lead would melt at about 300 something degrees Celsius. So the lead is still solid, okay? But after heating for some time, so that was originally one solid lump of lead, but after heating at 200 for some time, you begin to see some cracks generated. So the lead particle is broken up into many smaller ones, each one about 10 nanometers. So we think the mechanism is because of the lead diffusion. So the lead atoms from this lump is diffusing outside, all right? So for the spaces that become depleted of lead, that become the voids and looks like the cracks. Okay, so that is in a simple sentence, at 200 degrees Celsius, the original lead content will just diffuse away, forming this sort of maze-like structure. Quite interesting. At a higher temperature, so 700 degrees Celsius, the lead inside the copper would have melted, so become liquid. The copper is still copper solid, right? Then the lead content, as I said, would become more sheet-like, would become more plate-like, right, with reduced sphericity. So as we look at them, we saw a lot of plates. So all these spikes that you can see from there, they are not really spikes, they are sheets of lead. All right, so why is the lead doing that? Obviously, if you heat up to a high temperature, the lead will expand, will melt and expand, right? So the expansion actually causes a lot of stress. Okay, so if you have a small particle to start with, this expansion will stress up the neighborhood, and it will actually deform the copper. So therefore, the lead particle will now become a sheet. All right, so that's quite interesting. And there is certain crystallographic orientation relation between the lead and the copper as well. Okay, so that's quite interesting pathway that we have identified. This is another interesting experiment. So we heat up the brass containing the lead inside an SEM. Okay, so the white particles are the lead, and as you go from A, B, C onwards, the heating time or the heating temperature will go up. So as you do more and more heating, there are more and more white particles coming out. So the lead is trying to expose to the surface, diffuse to the surface. But at the later stage, you also see holes inside. So the surface now become very dimpled. There are holes. Why? Because after the lead has diffused out, you form a void in the material. Okay, so some examples, like if you compare this picture with that picture, if you look at the circle 3 here, circle 3 there is one more lead particle coming out. All right, And if you look at the cross-section of the sample, you see these voids. They are called diffusion voids. So the lead now comes out after heating, and then what is the fate of that? Well, the lead that has come out will quickly react with the surrounding water. We're immersing the lead into water, right, to study this leaching, to oxidize to become lead oxide. And the funny thing, the interesting thing is that sometimes these lead oxides become a sharp needle sticking out. So the growth of the oxide is highly anisotropic. It's not like a uniform, a smaller ball into a bigger ball, but it's highly anisotropic along certain crystallographic direction, which is this direction, okay? And of course, the needle cannot stand the current if the water is drifting around, so the needle would break, and that is what is causing the leaching. Okay, I think because of time, I will skip this part. There is also a study on the scaling formula. So of course, we can do all these studies on a small piece of sample, but you need a scaling formula to scale your result to a big system. Okay, so we are also developing this scaling formula to scale a small scale test result into the effects of a big system. The last slide now, which is also something that we are developing by one of our postdocs, Dr. G. He's looking at not pure brass with lead, but brass containing iron as well as lead. So basically, he found that when you have iron present, so these green stuff, they are the iron, they will actually hold up the lead. So that's why when the brass now contains iron, the leaching is smaller. So again, this is something quite interesting, right? So this could be some material that would still be useful for cutting, right, or for transporting water, but is more tolerant to leaching of lead. Okay, so that's my last slide. Concluding remarks. So Hong Kong is not that relevant to what I've just talked about, but we have a long history of supplying water, okay, dating back to 180 years. While we should use the best technologies available worldwide, some of the problems we faced are unique, especially the toilet flushing seawater, and require in-house solutions. So there is not much use looking at what USA is doing, what UK is doing. We have to find our own solution. And for that, government and universities should work closer together. So with that, I will stop. Thank you very much.